Now let's look at another way to do proofs, and that is proof by contraposition. So up until now, we've been solving proofs using direct methods, or performing what are called direct proofs. And that was things of this form: if P, then Q. But there are times when we may not know how to get directly to something, and we may look and realize if only we had, not Q, then we could do something with it. And so what we're going to do is make use of what we saw when we were talking about logic. Remember, we saw that P implies Q was equivalent to not Q implies not P, right? And so that was called contrapositive or contraposition, right? These are equivalent. So that means now we're going to set the problems this way and solve them. Another place where you might use proof by contraposition would be this. You have a biconditional. Remember we said something like P if and only if Q, which you wrote like this. This was a shortcut, right? Because this right here really meant P implies Q and Q implies P. So where does proof by contraposition come in? Well, maybe we prove P implies Q, and now instead of proving Q implies P, we'll do this right here. We replace this with not P implies not Q, and so we just show P implies Q and not P implies not Q and get what we need, okay? Be careful not to confuse P implies Q with its converse, which is Q implies P, okay? Why are those not the same? Well, we can set up a truth table and show they're not the same, but then we can give an example and say something like this. If an animal is a dog, then it is a mammal. Right? But we can't then conclude that if we're looking at a mammal, it must be a dog, because it might be an elephant, might be a monkey, could be a whale, any other mammal, right? So these two are not equivalent. Okay? So let's look at a couple of examples. So start with this. Prove that if n squared is odd, then n is odd. And so that would be like this. N squared is odd implies n is odd. Now I may look at this and think, well, I'm going to perform a direct proof. Okay? And so when I'm thinking direct proof, I may look at this and say, well, I know what n is, if n is odd, so I'll do something like this. I say, okay, if n is odd, I can write it as n is equal to 2k plus 1, which means that n squared is equal to 2k plus 1 times 2k plus 1, which is equal to 4k squared plus 2k will be plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1, which is odd. But what's the problem with this? I didn't really prove this. Instead, what I just did was this. N is odd implies that n squared is odd. Okay? So it turns out that is true, which I just showed here, but that's not what we're trying to prove. So, like I said, if I want to prove this, what I did is fine, but that's not what we're trying to prove. So what do we do with this? Well, if I was really trying to do a direct proof using the fact that n squared is odd, I do this. I say, okay, well, n squared is odd means that n squared is equal to 2k plus 1. And now what do I do with it? Well, then I could take square root of both sides and get n is equal to square root of 2k plus 1. But is that odd? Man, I don't know what to do with this. So a direct proof done correctly, at least in this form, doesn't really work for me. And so this is where, as we saw when I did this direct proof, knowing something about n is actually more useful. All right, so what's the contrapositive? So n squared is odd implies n is odd. So the contrapositive is that, and I'm going to abbreviate some of this, n odd not implies n squared odd not. What are these? What's the not of n is odd? Well, n is even. N even then implies that n squared is also even because this is a not. So this is pretty easy to do then. N, if it's even, can be written as 2k, where k, and I should have been saying this, remember, k is an element of the integers, here and here, okay? So n is equal to 2k, which means that n squared is 2k squared, which is 4k squared, which is 2 times 2k squared. This right here, of course, is an int. So 2 times some integer means this is even. And I've shown this, and because of contraposition, I've also proven this. All right? If you're still not clear why this is the correct way to do this, give that a little more thought about why I didn't really prove what I intended to prove here. Let's look at another one. If P and Q are positive real numbers, now we're not even limited to integers, are positive real numbers, such that the square root of PQ does not equal to P plus Q over 2, then P can't be equal to Q itself. So I have to admit, I saw this as an example in a book, and I was like, wow, I'm not sure what to do with this. But it turns out the contraposition of this actually makes what it's asking much more clear, I found. So what's the contraposition of this? Or the contrapositive? So we're saying if, before we do the contraposition, the original one, if the square root of PQ is not equal to P plus Q over 2, then P is not equal to Q. So the contraposition of this would be P is equal to Q implies square root of PQ is equal to P plus Q over 2. All right? So what do we do with this? Well, P is equal to Q, so now I'm going to take this. Square root of PQ is equal to square root of P times P, which is equal to P. And if we do the replacement over here, they have P plus Q over 2 is equal to P plus P over 2, which is equal to 2P over 2, which is P. There's P, there's P. Therefore the same. And like I said, once I rewrote it this way, this actually made more sense. Because if these two things are the same, we're simply just squaring P, taking the square root to get back to original P. And half of 2P's, like I saw here, really is just P. Okay? Let's look at another one. If n is equal to AB, then A is less than square root of n, or B is less than or equal to square root of n. Okay? And we have that A and B are greater than 0. So if I want to do some type of direct proof, I would have to think about what are all the different cases. So we have A is less than or equal to square root of n, and B is less than the square root of n. But think about all the different things we have, A or B's. So let's go through some of these cases. Case 1. So a is equal to square root of n, b is equal to square root of n. What do we get? AB is equal to square root of n times square root of n, which is equal to n. Okay, so a less than or equal to square root of n, b less than or square root of n is equal to ab. We can produce it that way. And an example with some example numbers here might make this a little more clear. This is not a proof in itself, but it helps us understand what numbers we're working with. Assume n is equal to 100. So square root of 100 is 10 times 10. Okay, so that works out. Or square root of 100 is, so I have 10 times 10. Okay, what's another case? A is the square root of n. B is less than square root of n. Okay, so what does that mean AB is? Well, we have the same A we had before, but now we have a smaller b, right? If b was equal to square root of n here, and now b is less than that, then that means we can't get n anymore. We have to get something that's less than n, because these are still positive. Remember, we're not dealing with negatives. So this would be something like 10 times 9 is 90. So let's say this right here was 10 times 10 is equal to 100. This would be something like 10 times 9 equals 90, which is less than 100. Case 3, a is equal to square root of n, and b is greater than square root of n. So once again, this is like 10 times 11, which is 110. The logic's the same as it was before. We had the same a, but now our b is greater than square root of n, so the overall result has to be greater than what we had before, which means it's greater than n. Okay? And so we could keep working these cases. Now, in many cases, we can put an equality or an inequality. We have a couple more cases. And when I worked it out, I found 9 total, but I don't write all these out. But let's look at case 8. A is less than square root of n, and b is greater than square root of n. So what is this relative to n? Well, it depends, you know. It depends on the values. If I have 9, which is less than the square root of 100, which is 10, and I have b as 20, well, then it's larger than n. But if I had, say, 1, and I have 11, well, that's only 11 total. That's less than n. So, once again, it depends. And likewise, for case 9, we could have a is greater than square root of n, and b is less than square root of n, and the logic's the same. Okay? So we can work through all of these, but man, that's a lot of work. What's the contrapositive of this? All right? So if, remember before we had if n equals ab, then a is less than or equal to the square root of n, or b is less than the square root of n. So now we swap and negate. So square root of n or b less than or equal to square root of n, not then n equals ab, not, or remember De Morgan's for this one. Remember De Morgan's when we talked about logic? So we'll do it over here. So remember we had something like this. A or B not was equivalent to not A and not B. So I'm going to use that here. So that means now we have A, what's the not of this? Well, A has to be greater than square root of n. And same thing for this. But now we have an and. So if, and the not of n is equal to AB, is that n is not equal to AB. All right? So how does this work out? Well, here we have A greater than square root of n, and we have B greater than square root of n. Well, let's think about how this would work. So if I had something like this, 2 is less than, we're using, or let's do greater than to match up. If I had something like this, 2 is greater than 5, and I have 5 is greater than 2, and I have 7 is greater than 3. Well, if I multiply these together, I get 35, and multiply these together, I get 6. The inequality is maintained, right? Because think of it this way. If I have 5 is greater than 2, and I multiply both sides by a, and a is positive, then we still know that 5a is greater than 2a, right? Say a is 1, we still have 5 or 2. A is 2, we have 10 is greater than 4, and so forth. Well, in this case, I'm multiplying by something even greater. Okay? So that means if I multiply this side by b, and multiply this side by the square root of n, then I still have the greater than. In fact, it's even more of a difference between the two. But this side right here is equal to n squared. Or excuse me, n. Okay? So AB is greater than n, which means AB is not equal to n. Okay, because we could swap these, right? This is AB not equal to n. So AB greater than n shows that AB is not equal to n. And this is arguably much easier to do than the top thing, although, at least for me, trying to understand what the problem was saying, looking at some of the different cases was helpful, but it was difficult to prove what was going on here. Okay, especially when you start getting into all these depends type things, right? So that was proof by contraposition.